Well, hello, everyone. Thank you for joining us today on this special holiday edition of EREF's Science Sessions. My name is Bryan Staley. I'm president of the foundation and glad to welcome you all today for this exciting topic of continued discussion around PFAS. A number of our science sessions have been on this topic, and since this is the holiday edition, I guess we could think of PFAS as the gift that keeps on giving, perhaps not in a good way. So as we get into this, we're going to talk about some of the advances in research around how we manage PFAS, particularly in landfill leachate. So before we get started, just a few housekeeping items. If you are trying to talk, you are muted. That is on purpose. If you have any questions for our speakers, please use the question function, and that will be in the control box for our GoToWebinar platform. And we will be mindful of those questions and do our best to get through all of them if in the allotted time that we have. If you do have a technical issue, please use the chat function and an EREF staff member will assist you. To access slides from today's presentation, take a moment to locate the handout section in the control panel, and there you'll find a PDF document available for download. If you would like a certificate of completion, which can be used for documenting continuing education credits, if you are a licensed professional, be sure to attend the entire webinar, and a link to that certificate with an evaluation survey will be provided early next week, along with a link to the recording of the session. So a couple of other things for those of you, if you're not familiar with EREF, we are a 501c3 research foundation. We are a grant-making organization, and we do that through a variety of different programs. A grants program, which primarily serves academic researchers in that space. We also do internal research through our data policy program, provide scholarships to graduate students, as well as translate all of this information into educational materials, such as the science session that you are sitting in right now. These sessions are structured to be more conversational, but we are focused on wanting to make sure that you get the best information possible and the most cutting edge information possible around what's happening on a variety of research topics. We can't do that without our session sponsors, and we'd like to thank them for their continued support of the science sessions this year. If you are interested in supporting this effort, we'd love to hear from you. Feel free to reach out to us, and we'd love to get you hooked up as a session sponsor. And then lastly, this is our last science session of the year. We will return in 2022. A couple of thoughts about that is while PFAS will continue to be an important topic, no doubt, we'll have science sessions related to those topics, but we are going to be working on evolving a broader platform in our science sessions to incorporate broader integrated waste management topics around research, including things like circular economy, sustainability, recycling, composting, waste to energy, and so forth. So stay tuned for that, and we will be putting out a slate of topics in early 2022. So with that, we have a couple of esteemed speakers today, and what I find interesting is the topic of today's session is treating PFAS using AC and DC. And I'm a child of the 80s, so I was really hoping that we could play like Thunderstruck or something during the introduction. But outside of that, I'm pleased to introduce a couple of our esteemed speakers today, Dr. Tom Holsen, who is the Gene S. Newell Distinguished Professor in Engineering, which is a professor in the Environmental and Civil Environmental Engineering Department at Clarkson University. He's also the director of the Clarkson Center for Air and Aquatic Resources, Engineering, and Sciences. Has published over 200 publications and has successfully supervised research projects from industrial sources and state and federal agencies. We'll get into what some of Dr. Holsen's research interests are in a minute. But before we do so, I'd also like to introduce his colleague, Dr. Yang, who received his PhD from Tsinghua University in 2014, did some postdoc work at California Institute of Technology, and then fairly recently, a couple of years ago, joined the Department of Civil and Environmental Engineering at Clarkson University and has been working on a variety of research topics, which has led to the publication of over 26 peer-reviewed articles as well as a number of patents. So, but before we get going on that, this is the topic of PFAS. I think most of you are likely familiar with this topic, but these are substances that are known as forever chemicals. there have been a number of recent developments on the PFAS front that are kind of moving the policy front forward. Recent research that suggests these chemicals do pose perhaps even more of a threat than most of us think of. And there's additional work on the policy front that may result in additional regulation. So this topic is very pertinent, and how do we deal with it, especially from engineered facilities like landfills, and dealing with landfill leachate is particularly important. As you all know, or may know, the EPA had provided some guidance early on that suggested to manage PFAS, it should either go to a landfill, be deep well injected, or be incinerated. All of those endpoints have some potential concerns around them. There's not as much research as we would like to address some of those concerns, and therefore there's been a lot of focus on advancing the science to better understand what's happening and how we deal with those particular challenges. Of course, landfill leachate is one of those particular components that are dealt with in terms of landfill management. And PFAS is one of those components that has been found pretty routinely in that landfill leachate. And so with that as a brief introduction, let's bring on our speakers. Tom Holsen, Yang Yang, why don't we get you all started with just maybe describing a little bit about your background and how you came to be interested in something like PFAS. Tom, can we start with you?
Sure. Let me start by thanking Brian and Kate for allowing us to share our research results today, and also supporting our research. Some of the results that we'll be discussing are directly supported by EREF. So my plasma story, PFAS plasma story, started about 6 years ago. I was part of an EPA-funded project to investigate point-of-use water treatment with 2 other faculty members here at Clarkson, Chris Bologna and Selma Medvedevich-Taggart. Chris was a membrane expert, and Selma did her PhD and continued to do research on plasma treatment of water. And we were investigating traditional contaminants at the time, not PFAS, but I had another PFAS project looking at PFAS in the Great Lakes, particularly in the Great Lakes fish. And so just by happenstance, we decided to put a few PFAS chemicals into one of our reactors that we were doing plasma treatment on, and we were quite surprised to see PFAS was removed better than any of the other contaminants. And of course, we didn't believe initial results because we knew PFAS were difficult to destroy, but over about the next year, we figured out that indeed we were removing these contaminants, breaking them down to fluoride and other short chain molecules, and started optimizing that process. So we've been working on this for about 5 years now.
And Yang, what's your story? How did you get involved in this topic?
Yep. Yeah, I would also like to thank the support of EREF and Bryan, give us fantastic opportunity. So actually, PFAS to me, it's like a old pal. So it's not a very new topic. It just brought public concern very recently. So in fact, I published my first PFAS paper in 2013. That was actually focused on the analysis and identification of new emerging PFAS in China. And during that period, one of my colleagues was actually doing electrochemical oxidation, treating PFAS. And to the best of my knowledge, the first paper focusing on using electrochemical oxidation to treat PFAS actually was published around 2003 or 2005. So it's pretty honestly, it's not a very new topic. So we accumulate enough knowledge, and we know how to do that, and we know the hiccup. Now it's time for us to overcome those hiccups. So after finishing my PhD, I moved to Caltech, and where I got a chance to work on electrochemical oxidation method, and also how to scale up the process, how to design the electromaterial. I'm very thrilled to be able to join Clarkson. After upon my first visit, Tom showed me this cutting edge and analytical equipment for PFAS analysis. It's already there, so it is very attractive. I just can't resist to just bring my specialty on electrochemical oxidation with Tom's strengths on PFAS analysis. So it's just a perfect, it's a happy marriage between me and Clarkson and Tom's group. Ever since that, I think, it's great. It's a great opportunity that everybody start to realize the PFAS is important. It's a big concern. So ever since joining Clarkson, we sort of we make further invention on electrochemical oxidation treatments, and we received several federal grants, and I greatly appreciate that. Of course, we are also supported by EREF. So I think it's a great opportunity for junior faculty like me, and under the tree already planted by Tom. And yeah, that's my story.
That's great. Well, I appreciate you all sharing that. It's always interesting to hear the path that kind of leads to where people are at that particular moment. And so with that, let's jump into the research that you all are doing. Tell us a little bit about the technologies that you're exploring in your research, and specifically, I know these revolve around the idea of plasma treatments, and maybe for the benefit of the audience, give us an overview of what plasma is. It sounds very sci-fi, and maybe just a brief overview of just generally how do you even make plasma, perhaps, and then why would one consider that as a form of PFAS treatment, and then perhaps get into some of the specific technologies that you all are exploring in the research. Do you want to take that one, Tom?
Yeah, sure. I'll start there. So plasma is something everybody's familiar with. Neon lights are a form of plasma. Lightning bolts are a form of plasma. So it's used a lot, used widely to make semiconductor chips, etching. So it's a well-known, well-understood technology applied more recently to water treatment. The strength of plasma generation is that it can generate not only oxidizing species, but reducing species. And it turns out PFAS destruction requires reducing conditions in general. So plasma allows us to break the carbon-fluorine bonds and reduce the PFAS to smaller molecules. The technology is actually pretty simple. We charge capacitors and then discharge them from a high voltage electrode. The ground electrode is in the water, and this generates plasma over the surface of the water. We do this at a pretty high frequency, about 60 times a second. And then we couple this with unique property of PFAS molecules is they're surfactant-like. So we can concentrate them at the air or the gas-water interface using bubbles. So we use argon gas, so we can control the chemistry, bubble that gas through the water, bring the PFAS to the interface where we generate the plasma and break down those molecules.
One quick question for you. So when you say reduction is needed to break the organic molecule, for those of us, it's been a while since we were sat in water chemistry class. Give us a quick 101 on what that means to reduce a molecule, if you don't mind, and how does the plasma proctor that?
Yeah, it's all, so you can either oxidize or reduce molecules by adding or subtracting electrons. And so we generally oxidize things. Chlorine is a good oxidizer, for example. We're familiar with those kind of processes. So this is just the opposite, to take electrons away from a molecule and break the bonds. And it's fairly familiar in chemistry. We do it all the time, but oxidizing is the more familiar process. Reducing is less common. It would happen in the absence of oxygen. Reducing conditions are in like sediments, for example, where we produce hydrogen sulfide. That's also reducing conditions. So happens in the environment, although environmental conditions generally aren't strong enough to break a carbon-fluorine bond.
Okay, so maybe to put this in a different way, tell me if my description is wrong. So in order to reduce something and to break those bonds, you need electrons, and electrical current is by definition is a flow of electrons through wires, and plasma is also a form of electrical current, if you want to think of it that way. So the plasma in essence is providing the electrons that allow for these molecules to be broken apart or reduced. Did I characterize that correctly?
Yeah, I think that's a good way to look at it, right? The gaining of electrons is a reduction process. So we generate those aqueous electrons, and they react with the carbon-fluorine bond and can break it.
Okay. Okay, great. That's very helpful. So in your research, then this I've got a, if anyone's looking on the slides, perhaps I've got a slide now that shows the experimental setup. Is this a good time to maybe take what you just said and kind of walk us through this experimental setup?
Yeah, sure. So the upper left is kind of a cartoon of what I just described, where we input gas into the bottom of the reactor, bring those PFAS molecules to the interface where there's a high voltage electrode. We discharge small, what looks like small lightning bolts. They're not thermally as hot as lightning, but they do generate ionized gas, and that gives us the electrons we need. In the middle is a picture of a reactor in operation. You can see that dark liquid on the bottom is actually leachate. In that reactor, we have a bunch of high voltage electrodes shown in the upper right. And then in the bottom cartoon is just a schematic of how we might break those PFAS molecules down at the interface.
Okay, and so the crux of the experiment that you're working on then is that in essence to refine and optimize this technology?
Yeah, exactly. So this you're looking at a reactor that's probably holds about 1 liter of water, and it's in a batch mode. So we're looking at increasing that to flow-through reactors. We have reactors now that are about 125 gallons and hydraulically can operate at about 10 gallons per minute. So we're trying to optimize this process and get it to be usable in the field.
Okay, and then so the counterpart technology that you're evaluating is this more of this electrochemical treatment. Is there what's the difference between the plasma treatment and sort of electrochemical oxidation? Or are we really talking about two sides of the same coin here?
Yeah, I think it's our technology is just exactly at the opposite side of Tom. So Tom used alternative current, and our process is driven by DC current. And the principle of plasma is to create a reductive environment, but in our case, we're trying to grab electron from PFAS. So the experimental setup I already showed here, this is a typical setup which we use, just a beaker, and anode and a cathode. So if you apply a 2-volt voltage between anode and cathode, you will see bubble, right? So the darker one is anode, and the bubble associated with it is oxygen. The cathode, the bubble you see on the shiny stainless steel cathode are hydrogen. So how it works? So if you look at PFAS structure for most of the PFAS of concern, like sulfonate with PFAS with sulfonate group and carboxylate group, they are usually deprotonated. That means they are negatively charged. All right. So our basic high school physics tell us that if you have a positively charged surface, the negatively charged molecule will tend to absorb on it. Right. That's exactly the first step happened. And according to thermodynamic calculation, we all know that the degree of oxidation is solely dependent on the reduction potential, right? So the higher the reduction potential, that means a higher level of oxidation reaction could happen. So to give you a number, in order to oxidize water to oxygen, you need about 1.2 volts. There is simulation shows that if you want to oxidize PFOS, then the anodic potential would be 5 volts. So in that case, if you can make sure that PFAS is absorbed on the electrode, on the anode, and there is enough high voltage applied on the anode, you can drag electron out of PFAS, right? So PFOS is the most challenging one. If you can get rid of PFOS, you can get rid of other type of PFAS with some part of the fluorine substituted by hydrogen. So what happened when PFAS, for example, PFOS, lose 1 electron? Once it loses 1 electron from the sulfonate group, it will form a radical chain. right? And this radical chain is very unstable. It will be subjected to a series of self-destruction reaction, forming, we call it CF2 unzipping mechanism. That means every time, once it forms a radical, it will lose CF2 group to form a shorter chain PFAS. And the shorter chain PFAS will subsequently repeat the whole process, by absorption and direct electron transfer to form a shorter and shorter PFAS, and eventually till complete mineralization.
Okay, that's great. So you've got on the plasma side, you've got AC or alternate current. On the electrochemical side, you've got the DC current. Yeah, actually, this reminds me, I'm probably going to get my history wrong here in this discussion. I mean, you guys kind of sound like Thomas Edison and Nikola Tesla here. Tesla was a big fan of AC current, and Edison was a fan of DC current. So which one's best?
Well, I think that's part of the research we're trying to understand. We have, as we go along, we'll talk about the challenges in the plasma reactor and the strength of the Young's electrochemical reactor, and we're trying to see if we can marry those two together to take the strengths of both of them.
Well, that's a great segue. So why don't you all tell us a little bit about the specific objectives of the research, so that you want them to be synergistic. Do you see them working like together literally as a technology, or do you see one technology being separate and applied in one situation and a different technology being applied in a separate situation?
I think that's some of the outcomes of the work we're trying to do and try to understand that better. We I don't want to get too much ahead of ourselves, but one of the weaknesses of our plasma process is that the shorter chain molecules are much harder to get to the air-water interface or gas-water interface because they're less hydrophobic, less soap-like. And I think Jan will explain later that his technology is less chain length dependent than the plasma technology. So when we wrote this proposal and started this work, we were thinking that we could maybe use the plasma first, remove all the long chain PFAS, which we can do quite readily, and then move to the electrochemical reactor.
Okay, so let's dig into that a little bit then. So you mentioned using plasma to treat long chain. So tell us a little bit about what happens to the PFAS molecule as it's exposed to PFAS treatment. And again, I've got some results that you all shared with us up on the screen for those who are following that. So maybe walk us through that a little bit.
Yeah, sure. So the long chain PFAS, PFOS in particular, is the most hydrophobic generally of the ones we look at. So we can remove those in timescales of minutes. And as we decrease in chain length, we remove them slower. The picture you see on your screen, if people are looking at the screen, that's actual leachate treatment. So obviously the plasma process is also destroying other organics. That water or the leachate started out quite dark and lightened during treatment time. So it's not selective, and it'll destroy anything that's at the air water or the gas water interface. So we try to concentrate the PFAS there where they're removed. Much like electrochemical process Professor Yang described, we unzip the PFAS molecules, so we chop off the ends and produce smaller chain molecules.
Okay, well then that's a great segue into the electrochemical side. So Yang, tell us a little bit about some of the electrochemical treatment results that you all are seeing.
Yes, so we can also in the electrochemical oxidation process, long chain can also be removed within a scale of minute, but we more value its capability to remove short chain one because, as you can see, the electrode is completely immersed in the solution, so it's not surface dependent. For short chain PFAS, they are usually more hydrophilic. Our assumption is that since it is already negatively charged, no matter it is accumulating in the surface interface or stay in the water, electrochemical process will be able to capture them. So that's really the strength. This is some preliminary data. On the left panel, you will see PFBA. It's a 3-carbon fluorinated carboxylate, perfluorinated carboxylate acid. So as you can see, we first start treating the raw leachate. You will see a gradual increase of the PFBA concentration followed by the decrease of PFBA concentration. That means the system works. It's just a matter of time and or how we further accelerate the process. The increase of PFBA is because of the chop off of long chain PFAS to shorter one, right? While the reduction one is totally through the destruction pathway. So we're also trying to use electrochemical oxidation as a downstream process for the plasma treatment process. In the plasma process is able to completely convert long chain to short chain carboxylate acid, which we believe that we can use the strains of electrochemical oxidation to address the product they produce. So there are some early hope. As you can see in the orange line, there is a reduction of PFBA. So we are still trying to understand why the whole reaction become more sluggish. Hopefully the completion of the project will give us an answer or a solution. Same conclusion could apply to PFBS, which is a very challenging short chain compound. So our data shows that it can be removed. But again, we are confident that upon the optimization of the process, a faster removal or an enhanced performance could be achieved.
Okay, that's a good segue in terms of what in terms of these technologies being used, whether it's in concert or separately. You already alluded, I think, Tom, to the fact that the plasma-based treatment seems to destroy the longer chain PFAS a little bit more effectively. But let's dig into that a little bit more. I mean, what happens when these technologies are applied? Do they work with equal effectiveness, and maybe give a sense for when you might select one versus another, or should they be used kind of in sequence? Which it sounds like what I'm hearing, but maybe dig into that a little bit more for the audience.
Yeah, I think originally, and maybe we started thinking sequentially is the way to go. We've recently discovered that we can add a surfactant to treated water, long chain anionic surfactant. Cationic surfactant, which will bind with the short chain PFAS molecules and make them easy to transport to the interface. So now in this figure on the lower right, this is actually PFBS concentration with the surfactant addition. And so, although originally we were thinking plasma treatment would require no other additives to get at these shorter chain molecules, we've realized we do need the additives. We add a non-toxic surfactant to help bring them to the interface. Those surfactants are also broken down by plasma. Actually, they're broken down faster than the PFAS molecules themselves, since they just have carbon-hydrogen bonds. So here, I mean, the previous slide we showed electrochemical removal. Here we have plasma removal. So we're trying to understand to compare these two processes and see which is going to be the best one going forward.
That reminds me. I think I can give you some lab assistance. We have some pranksters in our neighborhood that keep adding detergent to a big fountain that's kind of at our entrance. And so when I know they've been at work whenever the bubbles are overflowing the fountain, and so that's the surfactant addition. I think I just need to send them up to Clarkson with some batteries and some source of electrical current. Maybe they can help you out there.
Or we'll sell you a plasma reactor. You can add it to your fountain to remove those surfactants when they add them.
There we go. PFAS removal research in progress. So with that, then let's dig a little bit into the electrochemical treatment results. Yang, you wanna walk us through what some of the new efforts that you all are working on are leading you to realize?
Yes. So I've already shown the removal of short chain PFAS. So now this slide shows how fast the PFAS of concern could be removed. So I'm a little bit hesitant to put a lower energy consumption compared to plasma here. Well, I will explain the detail. So anyway, PFOS and PFOA is not a problem at all. They got removed, no matter it is in plasma, in raw leachate, or they are in a form of residual component after the plasma treated leachate. But what that actually, so I also would like to address that since PFAS was removed within 10 minutes, there's no concern about disinfection byproduct formation in our system, because the chlorine produced simply will rapidly be consumed by other substrate like organics and a huge load of ammonium, right? So in that case, the removal of PFAS, long-chain PFAS like PFOA and PFOS by electrochemical oxidation seems to be a perfect solution. But if you look at, I'm not sure if you look at the next slide. So one fundamental question we are trying to answer is that, is it removed by just absorption or destruction, right? So it is very difficult to do such mass balance in leachate because of the low concentration of PFOS. So we managed to do that in a pure solution, just spiked with PFAS. So the result is not very exciting, because if we run the reaction at a high concentration, you will see that PFOS and PFBS, there are significant region marked in red. That means they absorb on the electron. They were absorbed. A majority of them were actually absorbed, not destroyed. We have to admit that we can still destroy them. Okay, it's just that they will absorb on it first and then gradually decompose. Promising side are those carboxylate group compound, PFOA and PFBA. They are nearly, as for PFBA, they are completely destroyed into fluoride. So there are a lot of interesting, this is an old area, but we are trying to gain more mechanistic understanding. We just don't want to throw our super good energy consumption number. Rather, we would like to see the fate of PFAS, both long chain and short chain, in our process. We are trying to really, we're working very hard toward completing the fluorine balance to give a clean answer. That being said, I'm not saying that removal, we can't destroy PFOS and PFBS, even if at the end of the project we prove that they are just removed by absorption, our electro product, we can make it, our electro product is durable for high temperature recalcination or all sorts of regeneration methods. So there are different ways to reach our goal.
So in terms of these results, then, as you apply the electrochemical oxidation or the plasma-based treatment, what is generated from this? I mean, are we seeing complete total destruction of the PFAS molecule where there's no sort of residual waste, or is there residual waste to be managed? And I bring that up just for reference because, and I know we'll be talking about how this compares to some existing technologies, but you know, one of the things with a lot of the technologies that are out there, especially when we talk about PFAS treatment, is that there is a residual still to be managed. So where do these technologies fit in terms of residual formation that still might require some additional level of management beyond the initial treatment using these technologies?
Yeah, I think we both answer this the same way. We both basically create shorter and shorter PFAS molecules. Eventually, if we treat long enough, we'll get fluoride and CO2, and you know, sulfate or other ions, rather inert ions that are left over. If you treat incompletely, then you'll get the effluent will contain shorter chain molecules, shorter chain PFAS molecules. Really, it's a trade-off between energy costs, treatment time, and what the effluent limits are that you're after.
Yeah. Okay. I do want to point out an arrow that the time scale showing here on the left panel is actually minutes, not hour. So
I had a question on that.
It's minutes, so blame the student. Anyway. Yeah, I do want to add that both plasma and electrochemical oxidation feature a simple design, so we don't need to. So the catalytic interface, they are all immobilized, so we don't need to recovered, for example, recovered powder, particularly catalysts. And I also want to highlight the effectiveness of the technology. When you put the energy inside, it's all converted to the power to destroy PFAS. There's no such issue like the interference of light absorption or something like that. So the third advantage would be room temperature, atmospheric pressure. We don't need a pressurized reactor. So I think Tom already addressed that, PFAS destruction become more and more challenging along the reaction pathway because it forms some shorter chain products. But eventually, if you want, eventually they will all become fluoride, as shown in this mass balance. In terms of residual management, I don't think our technology create any sludge or any waste, and I don't think plasma produce the solid waste problem.
Okay, and I'm glad you offered the correction on the graph, but I think that the question I had related to timing, Ben, and Tom, kind of to your point too, with enough time and with enough electrical current, you can completely transform PFAS to basically fluoride and some other ions. So the question that I think the elephant in the room question that I would have is how do you all have a sense now, and we may be way too early in the research, but do you have a sense now for how long it would take to achieve complete reduction of the PFAS to fluoride, and at what point? To me, I think I'm bringing up basically what would be a trade-off kind of question, right? Is okay, if it's going to take 1,000 minutes to complete reduction versus say 600 minutes, what's the trade-off there? There's still going to be significant concentrations of shorter chain PFAS that would still need to be dealt with, or kind of where are you at in that? Is there sort of an optimal treatment time frame that you have identified yet, or is that still something that's under research that you're still working on?
Yeah, that's a complicated question, and something we haven't talked about yet is precursor ions. So in these complex waste streams, there's lots of what we call precursor PFAS present. And those precursors get broken down into the PFAS we're familiar with in both of our treatment processes, and in fact, in the environment as well. So for a complex waste stream like this, we often see initially concentrations go up as we remove precursors and produce these alkyl acids and sulfonates that we're used to seeing, and then we remove them. So treatment time totally depends on if there's precursors present and in what concentration, and then these initial concentrations of these molecules as well. So there's not one answer. It depends on the waste stream we're treating. We know we can remove them. It's a question about how long it takes and what the treatment goals are. If you need everything below 10 nanograms per liter, that takes a really long time. If you're only interested in PFOA and PFOS, less than 70, for example, the current federal guidelines, that's pretty rapid.
I see. And that's helpful just to provide context. And so, I mean, in that respect, when you think about comparison to some of these existing technologies, where do you feel like these technologies fit relative to existing strategies like reverse osmosis, for example?
Yeah, that's another complicated question, and one we're working on. So there's really two ways to look at these kind of processes. First, you can concentrate using RO or nanofiltration, for example, and then treat destructively these concentrated solutions. In the case of ion exchange, for example, you can run an ion exchange process for a long time, let that water go, then regenerate the ion exchange resin, get that concentrated PFAS solution. That's a much smaller concentration, a much smaller volume, much higher concentration. Can be treated in a completely different system, and maybe in a batch mode, for example, and take a much longer time. So those are the questions we're trying to answer right now. We have projects looking at both ways, direct plasma treatment and using a concentration stream ion exchange or RO, for example, to increase the concentration of PFAS, then destructively try to treat a higher concentration, smaller volume solution.
Okay, so it sounds like you're looking then at, if we think of the leachate treatment train, you're looking at whether this could be included kind of in line with just the raw leachate, as well as looking at this as a possible residual treatment strategy from a technology like a reverse osmosis. Did I hear that right?
Yeah, exactly right. Yep, I think.
Okay. Oh, that's fascinating.
Yeah, I would like to add that in terms of electrochemical oxidation, we like concentrated waste because the more conductive the water, the lower the energy consumption for our system. So people might raise concern about fouling, deposition of calcium, magnesium, but that's an engineering problem, a challenge. We have the solution already. So my understanding for now is that the electrochemical oxidation welcome concentrate, either our concentrate or ion exchange regenerant. So we actually also have project digging in this area. So the preliminary data is very promising.
Okay, that's great. And so, well, that's great to hear all the different things you all are thinking about. In terms of your progress on these projects, I mean, where do you all feel like you're at? I mean, I know with the grant you have from EREF, I think we're sort of approaching sort of the midpoint, maybe early on still. Where do you feel like you're at in terms of this specific study? I mean, you feel like you're getting close to the place where we'll have sort of next steps outlined? Are there some experiments that are still in progress that you're not showing us that kind of give us some additional insight on how to whether to use it for RO residual or to put it in line with the regular treatment train?
Yeah, as far as this specific project, we are working. We treated about half of the leachates that we received from our industrial collaborators. They don't seem very different, to be honest. I think we're pretty confident now that we have a good handle on how to treat leachates, and removal works really well. We do have this one RO reject sample from leachate. The results shown on this slide, much more complex sample, lots of precursors there, clearly, because you can see things going up and down in concentration as we break down precursors and produce more short chain compounds, excuse me. But you do see even at this, so it takes a much longer time. Instead of tens of minutes, we're treating for hours. But the volumes are much smaller. So these are engineering questions that we I think we have the data to address, and we're moving towards hopefully doing some field demonstrations and investigations of these processes.
And now, you said something earlier that I wanted to kind of connect back to what you just said now, and you had mentioned that the plasma treatment process or the electrochemical process is not preferential, and even though the discussion is around PFAS, it's also removing other organics and other kinds of molecules. Can you not to put you on the spot too much, but can you speak to that a little bit? Would this particular technology, for example, be able to replace or perhaps reduce costs or treatment needs from some of the other technologies? For instance, could you reduce the residence time if you've got an activated sludge process if you put a technology like this kind of in line with the treatment train? Could this serve as another sort of form of treatment, or could it even replace perhaps some of the other treatment strategies? I'm just curious to get your thoughts. I know you may be speculating in your answer, but I'd be curious to hear what your thoughts are.
Yeah, maybe I'll talk about plasma first and then electrochemistry, because I think the answer is going to be somewhat different. The plasma process, as I explained, uses bubbling to concentrate at the gas-water interface. So It does not remove very well anything that stays in solution that can't be concentrated using bubbling.
Okay.
So that's a positive and a negative. It's a positive from a PFAS destruction point of view, because we don't have to deal with everything else that's in solution. But if you want to use it to treat something that's in the dissolved phase, it's quite slow and doesn't work very well.
So in terms of electrochemical oxidation, I think it's PFAS case dependent in terms of selectivity. As you can see, PFOS and PFOA, they have longer carbon fluorine chain. That means they have a tail that is more hydrophobic, and our electrode surface is somewhat hydrophobic. So they can easily absorb on it first, leading to a apparent removal, right? So though we are still trying to figure out whether they are destroyed or not. In that case, in that sense, it is selective because after running the system for like 5 minutes, you see removal, 1 log removal of PFOS and PFOA. There's literally no reduction of COD at all. So in that case, we can treat it as selective. It's a very good question that whether we could co-treat other substrates. So in fact, using electrochemical oxidation to treat leachate is also a classic topic. So people prove that by using this as a pre-treatment process, you can increase the BOD. That means that facilitate the following activated sludge process. And the beautiful part is that I like leachate is that leachate has a lot of chloride and ammonium. So electrochemical oxidation, one of the side reaction is to produce chlorine, free chlorine, oxidized chloride to chlorine. So, and we all know that there is a famous equation called breakpoint chlorination. So if you produce chlorine, you can convert ammonium to nitrogen. Right? Before the breakpoint, the formation of disinfection byproduct is not a concern. So that's actually a appropriate niche for the electrochemical oxidation process. Let's say we can convert the background organic to more biodegradable and also remove ammonium if we keep the treatment time long enough.
Interesting. Okay, that's fascinating. So, and I know a lot of the work that you're doing is very much in the experimental phase, but maybe tell us a little bit about bringing this sort of to the facilities, to the landfills. What do you think is needed in order to bring these technologies from the lab bench to the landfill?
Yeah, so Clarkson encourages faculty members to have startup companies. So Selma Moderator, who I mentioned before in chemical engineering, myself has a startup company called DMAX Plasma. And we have been in the field already, not at landfills, but at some DOD and industrial sites. So we're ready to go. We're talking to a large landfill operator right now, and hopefully we will be treating some leachate in the field sometime in 2022.
Great. Well, tell us a little bit about the different scales of these technologies then, and how you kind of got to that point, and maybe perhaps some of the configuration of the technologies.
Yeah. So PFAS is one of the project, but I have other projects focused on using electrochemical oxidation to treat other stuff. So like mitigation of harmful algal bloom, or just treating, or just use a electrochemical oxidation method to treat sewage wastewater produced from a community scale. So these are some picture that is not directly relevant to the PFAS pilot scale testing, but I think we can load this equipment to Tom's truck and then go to the leachate sites if Tom allow us to mess up the testing sites. Anyway, I think we have at Clarkson, we have the strong capability to do all kinds of things, including the manufacturing of large-scale electrode and large-scale reactors. So in this slide, we demonstrate bench-scale, mesoscale, and pilot-scale reactor. It's essentially an array of cathode and anode, and you find a case to hold to encapsulate, right? So, and there is the big black box there is a customized DC power supply. You can also get it from in United States. So in terms of electrode, we I demonstrated coupon size electrode in a beaker, but actually we can make larger scale electrodes. So below are some electrode in a porous style and electrode in a plate style, so we can easily scale them up. So in fact, I would like to take advantage of a video conference. So I don't need to bring this one to actual conference room. So this is the full size electrode we can produce. So scaling up is not a problem. I think one of the hurdle is that we know the electrode works for the treating other like harmful in the field of mitigation of harmful bloom and disinfection. The support of EREF is a big push for us to evaluate the performance of these kind of electrode on PFAS treatment. Once we collect enough data, the design, we can easily modify the design in, let the system stay as it is, or change the parameter to push it forward toward application. So it's promising.
Well, that's great to hear. I mean, you all are much further along in terms of the application than I actually thought you were. So that's really great to hear. So why don't we kind of wrap up with what if you were to share kind of like your key takeaways from this conversation with this audience, what would they be?
Maybe I'll go first with plasma treatment. I think it's now a proven technology. We've demonstrated in the field. Works really, really well on long chain compounds. And I think we have a way now to treat short chain compounds in addition. That might not be better than doing short chain compounds by electrochemical treatment. That's part of the project we're working on now.
So in terms of my research, I think it is for now, it is the time for us to further refine the research. So to determine whether they are removing by absorption or by oxidation, that's critical. That could affect the mode of operation, right? And then I would also arouse public attention on the issue of short chain PFAS. So they are the inevitable products. It is definitely more challenging to be removed compared to long chain PFAS. Yeah.
Great. So I think that wraps up kind of our formal conversation. Let's go to the, all right, make sure I stop my screen sharing here. Okay, so let's go to some questions from the audience here. And for those of you who are listening, if we did not cover anything that you're still curious about, now's the time to ask while we still have these gentlemen for a couple of more minutes. So a couple of questions from the audience. Are the reduced compounds generated by this process odorous?
That's a good question. When we do leachate treatment, the students tell me they smell pretty bad to start with, and by the end they don't smell as much. So that's the only evidence I have about odor.
Young, any thoughts from you?
Well, I typically don't go to the lab. Well, yeah, there are smells. So as you can see, during the electrochemical oxidation process, there will be bubble, right? So gas purging of the volatile fatty acid or hydrogen sulfide would be a concern. Also foaming. Really depends on type of the treatments. While Tom liked the foam, we don't. So because if you didn't leave enough headspace, it could overflow. It's not a matter of treatment, it's just a matter of cleanliness in the lab. So yeah.
Okay. And I think another question for you, Young, that's come in, and you may have addressed it, but I think it's asked a different way. What will happen for the precipitate in the electrochemical oxidation process if there are any short chain PFAS?
That's a good question. Actually, we don't see any precipitate because the mechanism simply, well, it's not phase separation. If you have to say that the formation of new solid phase, that would be actually the calcium magnesium deposit on the cathode, so which is stainless steel, because on the cathode you have hydrogen evolution, you essentially consume a lot of proton, elevating the regional pH that create a perfect condition for calcium, magnesium to be deposited. But that one can be easily addressed by reverse the polarity and let them drop. So that's during the treatment process, there's actually no solid. But after long run, you might want to take some measures to clean the cathode primarily. Yeah.
Okay. Let's see here. As far as okay, yes, what is the mechanism of CTAB in short chain treatment, or is it just absorption or reduction?
So CTAB is a soap-like molecule, so it has a hydrophobic tail and a cationic head. And that cationic head, we believe, can associate with the negatively charged PFAS molecules. And we believe the tails also, the hydrophobic tails also have some kind of interaction. So basically the short chain PFAS hitch a ride on the long chain surfactant molecules and go up to the interface.
Okay, and so one more question on kind of the fate of the products after treatment is what happens to the fluoride?
The fluoride just stays in solution. Generally the solutions we treat are quite low, and the PFAS concentration is nanograms or micrograms per liter. So you would convert that all that to fluoride on a molar basis times how many of our fluoride molecules or fluoride atoms are in the molecule. But pH changes. It's basically making hydrogen fluoride, but we don't see much pH change in these solutions. So it's not a concern.
Yeah, I concur that fluoride stay in the water as an ion. So I might show in the bar chart, I might show some fluoride escaping in the gas phase and captured by the washing bottle. That is just because we use a very high concentration PFAS. So the fluorine we produce approach to the acidic surface of NO and then become HF. That only happened when you were using a high concentration PFAS.
Okay. And we've got time for just a few more questions. Have you tried to pair plasma, EC, and UV technologies, such as the one presented in I think the previous science sessions webinar? But have you tried to pair those together? And if so, what did you see from that?
We've actually explored using the UV process for treating precursors before the plasma, thinking that might speed up the plasma process. But we found that the plasma alone is faster than the UV, so it really didn't help us much.
Okay, and then kind of more on the operations side of things, two questions related to operations. How often do the electrodes need to be replaced with these technologies?
That's very good. That's a very good question. So it really depends on the current density, how harsh you use the electrode and what is the material of the electrode made of. So far, I think according to our experience on other projects, I would recommend at least examine the electrode once a year or 6 months a year. That's based on my experience to other projects like sewage treatment or lake water treatment. In terms of PFAS, that's really a good question. So I don't have the exact answer, but the electrode could be durable. So you might need to worry about other parts like the power supply and the electronic connection than the electrode itself.
Yeah, and in the plasma process, we generally use tungsten electrodes. They're very, very durable, so we don't have to clean them or replace them, at least on time scales of months.
Okay. And then any safety concerns from the electrical standpoint for any operators, especially if they're not as well versed in these technologies?
Yeah, electrical, we use, we generate very high voltages, so we have to design our systems to be quite safe. We generally put them, inside boxes. If you open the door, the voltage is shut off. So that's always on our mind, and we take precautions to make sure people don't get exposed to high voltages.
Yep. For the electrochemical process, the voltage is usually below 20 volts. So if you 20 volt DC, so if you do appropriately insulate the electronic connection, that's not a concern.
Oh, gotcha. Okay. And last question then, about cost. Any sense for what the treatment cost would be for these technologies if they were implemented in the field?
Yeah, that goes back to what the initial concentrations are, flow rates, and treatment goals. I can tell you that for one of our DoD demonstrations where we were treating groundwater in the flow rates of 4 or 5 gallons per minute, the total energy costs were less than half a penny per gallon. So energy is quite efficient plasma generation. Our power supplies are about 1,500 watts for a 100-gallon reactor. So that's like a microwave oven. So it's not very energy intensive.
I have no exact answer to that question. So because we are still trying to figure out the problem just mentioned by Tom. But I can give you a quote. The big electrode I just showed is $200. And you might need tens of them, really depending on the treatment capacity you want and effluent concentration. And the typical high current DC power supply, 1,000 amp, the cost is about $6,000 US. You might also need a couple of them. So that's kind of the layout.
Okay. Well, very, very promising in terms of effectiveness as well as cost. And we're at time now. I'd like to thank you, gentlemen, very much for your time today and appreciate you sharing with us what your efforts have been. Look forward to hearing more about how the research continues to go. And thank you to our sponsors, and thank you who have attended. This will conclude our science session, and hope you all have a great holiday season. Happy New Year, and we will see you all in 2022.
Okay, happy holidays. Thanks again.
Thank you. Happy holiday.